Good morning, everyone, and once again, welcome to the 5th Emerging Researchers Symposium at the CSIR conference. Like said, my name is Tshiamo Segakweng, and today I will be presenting on the effects of using different organic linkers on the hydrogen storage ability of zirconium-based metal organic frameworks. It's quite a mouthful. The objectives of this part of my work are to prepare metal organic frameworks using different organic linkers and via different synthetic routes. And then we'll investigate the influence of the different sized organic linkers on the hydrogen stability, on the hydrogen storage ability of the MOFs. And with that understanding, we'll use that together with the understanding that we gather from the other parts of the research to maximize the hydrogen storage ability of our MOFs. Just an introduction about where I come from. I'm part of our group is CSIR, which is Hydrogen South Africa, and then it's an initiative by the DST to increase hydrogen, to create a hydrogen knowledge base in South Africa, as well as to create a hydrogen economy in South Africa. Now, I am part of the hydrogen CSIR infrastructure, which is hosted by the Northwest University and the CSIR. Just a short story on the story of hydrogen storage and why it is such an important thing to research and to try sort out. Currently, people have been using fossil fuels for energy, and the problem with that they've given a lot of environmental problems. So we've been trying to look for alternative energy sources, and of the different energy sources that are available, hydrogen seems to be the only one that is promising for onboard storage applications. And by onboard, I mean use in cars, trucks, and yes, such appliances, as opposed to your stationary applications, which would be your powering your houses and the smart cities. Now, hydrogen has a huge, high energy content as opposed to other energy sources, and it's the one that can produce energy under near ambient conditions, unlike your your nuclear and solar, which solar requires a huge space to work, and your nuclear, the danger applications of that. But the one problem with hydrogen is that it is very light. It has a very low density, which results in that for us to have enough hydrogen, for example, for a car, for an electric vehicle, to cover the same mileage that a petrol car covers, you need the volume that is enough to fill a room with or a sphere with a 5-meter diameter, which is impractical for onboard applications. Hence, they need to find ways to store the hydrogen and be able to release it when needed. Now, of the methods that are available, you can store it as a compressed gas, which obviously high pressures in a car, they have their own disadvantages. Mainly the safety aspect, and then then you have metal hydrides, which the disadvantage of metal hydrides, they require high energies for storage and release of hydrogen and are very heavy. Then you have your metal organic frameworks, which can store and release hydrogen at lower temperatures. But the only challenge now is to get hydrogen to store energy at near ambient conditions. Currently, the metal organic frameworks have been able to store hydrogen at cryogenic temperatures. The MOFs that we'll be talking about today is the Zirconium-MOF, and the two linkers that I've used for this part of the work is the terephthalic acid and fumaric acid. The MOF that we synthesize using terephthalic acid, I have denoted Zr-BDC, the BDC from the terephthalate ion, and the fumaric acid, I have denoted Zr-Fume MOFs. That's just the acronym for the fumarate ion. Then here we have the structure of the two MOFs with these yellow spheres here, denoting the space available for gas molecules to be occupied in. Just some background knowledge on the effect of using different linkers. It is known that the kinetic diameter of hydrogen is almost 3 angstroms. And for you to have micropores that have the highest hydrogen storage, you need the pores of those micropores have to be slightly higher than that, which is about 6 angstroms. The reason for that is that having pores that are slightly above or close to 6 angstroms will strengthen the interactions between the hydrogen molecules as well as the pores of the metal organic frameworks. Now, one way of getting those smaller pores is to use a shorter linker. In my case, the terephthalic linker from the terephthalic acid has a length of 7.01 angstroms, and the fumarate MOF has the fumaric acid has a diameter of a length of 5.11 angstroms. And we were expecting that using the shorter linker, being the fumaric ion linker, would result in smaller pores, which would, as explained, result in higher interactions with the hydrogen, and so higher hydrogen storage. The way we synthesized our MOFs, these two MOFs were synthesized using a isothermal synthesis with DMF as the solvent. Our metal salt solution, which was used to introduce the metal salt zirconium, was zirconium chloride, and our organic linkers were simply dissolved in the solvent DMF. The crystals were grown at 120 degrees with varying times from 1 to 24 hours, just to investigate the optimal time to grow the best crystals and get the best hydrogen storage. Then from there, the samples were recovered and we performed a solvent exchange, and samples were dried and analyzed. To our results, we see that on this side we've got the zirconium fumarate MOFs. They do show the intensity of the peaks from the 1 hour synthesis all the way to the 24-hour synthesis is relatively good, as well as the zirconium terephthalate MOFs. The only main difference that we observed from the two XRDs is just the peak position, whereas in that the zirconium fumarate MOFs had a peak shift of about 1.5 degrees as opposed to the zirconium terephthalate MOFs. Then from the same images, you can see that from the 1 hour synthesis right through to the 24-hour synthesis for our zirconium terephthalate MOFs, we've got regular octahedral shapes, and the same can also be seen for the zirconium fumarate MOFs. This indicated that we did have the MOFs that we wanted, but the only difference being the shapes would be the sizes or pore volumes and pore sizes of the two MOFs would be different. But we did not expect different shapes, and that is exactly what we did get. Then the next step was to investigate the surface areas and hydrogen absorption. For the surface area and pore volumes and pore sizes, we did a nitrogen absorption on our ASAP 2020 instrument. Then we can see from here that the zirconium terephthalate MOF, being the Zr-BDC, absorbed more nitrogen than the zirconium fumarate MOFs. This already can give us an indication that the surface area of the zirconium terephthalate MOF is higher than that of the zirconium fumarate MOFs. And from there has been a direct correlation shown between surface area and hydrogen absorption, in that we would expect the one with the higher hydrogen, the higher surface area to absorb more hydrogen. And that's exactly what we got this side by seeing that the zirconium terephthalate MOF, shown in blue here, absorbed almost 1.5% hydrogen, and this is at 1 bar and at a temperature of 77 Kelvin. Whereas the zirconium fumarate MOF only absorbed about 1.3, just above 1.2% hydrogen at the same conditions. Now, this is not something that we had expected initially, in that we thought this zirconium fumarate MOFs with the shorter linkers would absorb more hydrogen. But then that can be explained when you go and further see the pore size distributions of the two MOFs. Here we have the zirconium terephthalate MOFs. The pore sizes, they show the pore size of 1 to 3 micrometers, and the zirconium fumarate, these are for the 24-hour synthesis, had a particle size of 100 to 200 nanometers. Then the surface area, the BET surface area, as expected, the zirconium terephthalate MOFs had higher hydrogen adsorption. The interesting part comes to here when we look at the pore width, in that for the terephthalate MOFs, we've got two distinct pores, which is one at 7,8 and one at 11 Armstrongs, as opposed to the zirconium fumarate MOFs, which had only the pore size of 7,1. The reason being that from the same images, we could see that the degree of interpenetration between the crystals of the zirconium terephthalate MOFs was much higher. And that interpenetration results in higher surface area and a restriction in the pores. If there was no interpenetration, we'd only have a pore size of 11 Armstrongs, which would then result in a lower hydrogen storage. But because of the interpenetration, we see that some pores, the pore size was restricted to 7,8. And that, together with the increased surface area, resulted in much higher hydrogen storage, as shown there. Next, the TG analysis showed that both MOFs are stable up to about 550 degrees, which is what we had expected. Then we ran stability tests to test the stability of the two MOFs in different environments. And we can see that in deionized water and acetone, dried acetone, over a period of 24 hours, the PXRD patterns of both MOFs did not change. In conclusion, we were able to synthesize both MOFs successfully using the two different linkers. And we did notice that a choice in linker affected the hydrogen storage, not just in terms of the pore sizes, as we saw that we also had other effects coming into play, such as interpenetration, which resulted in the MOF with the larger, which used the larger linkers, had a higher hydrogen adsorption. That's because of those extra effects, factors that came into play, being primarily the interpenetration. Then one thing that we still need to investigate is the possibility of improvement of the hydrogen storage at higher pressures, which is part of the ongoing research. We have not been able to do this as we only got our instrument recently commissioned. With that, I thank everyone, our sponsors and my supervisors, Dr. Ren and Dr. Lange. Thank you very much.